Before watching this video, you should know that this is actually a segment of a larger video series called the Ultimate Linear Algebra Guide, where I cover each concept more in depth with larger videos and have problems and solutions attached to each video that you can work through. The resource is completely free, but the videos themselves are a little bit longer, so it takes me a while to make. Go ahead and check the description if the linear algebra guide video for this corresponding concept has already been released. And if it has, go ahead and check it out because it is the better resource. Otherwise, until it does, you can stick around and watch this video. Make sure you subscribe and turn notifications on so you'll know when I do release the corresponding Ultimate Linear Algebra Guide. And with that, we can get into the video.
Okay, so when solving a system of linear equations, we have three cases. The first case is the one that we explored in the previous segment, where the system has one solution. You should have already got some practice with this case from the practice problem, so I'm not really going to go over it again, but that's the first case that you've already learned. The second case is that the system of equations has no solution. This is the one that we're going to focus on in this segment. These two systems of linear equations have no solution. I'm going to teach you how you can identify this alongside how you can represent it in a form of a matrix. So let's get started with this system over here. So in the previous video, we've already worked with a system of linear equations, but there we had three variables. Here we have a 2x2 system. So I just wanted to show you that you can also use Gaussian elimination to solve a 2x2 system just as you would a 3x3. But you could probably do this in other methods, like the one you've probably learned in your Algebra 2 class, and you don't really need a knowledge of linear algebra to do so, but it's all the same to Gaussian elimination. And another thing is, you can probably already tell intuitively that this system has no solutions. Because if you take this equation right here and you multiply it by 2, you will get 2x plus 2y is equal to 4. So this doesn't match with our second equation. So it's possible that this system has no solutions. And you can probably already see that. Because if this says one thing and this gives us another piece of information, since those two don't match, we probably don't have a solution to this system of equations. But let's move on to how we can actually identify that using Gaussian elimination. So let's represent this as a matrix, a coefficient matrix, and let's just try applying Gaussian elimination to it. So the first column, this is just like a 3x3 matrix, except it's a 2x2 because we have a 2x2 system of equations. The first would represent the coefficients of x, so 1 and 2. The second would represent the coefficients of y, so once again, 1 and 2, and we can add on the values that these equations are equal to. So x plus y is equal to 2, and 2x plus 2y is equal to 5. So now let's go ahead and put this into the row echelon form so we can identify that this has no solutions. So here for us, and this is not always the case as we saw in the previous example, but here we already have our first leading one along the main diagonal, so all we have to do is create the second one. But before that, we need to eliminate this 2. We need to make this 2 a 0, so this can be the first term in the row. So let's go ahead and do that. To do that, I see that in this column we have a leading one right above it, so we could probably subtract 2 times this row from this row in order to eliminate this term. So let's go ahead and do that. So if we subtract 2 times row 1 from row 2, we get, well, the first row stays the same since we're only affecting row 2 of our matrix, but the second row will change. So like we intended, 2 minus 2 is 0, but again we get 2 minus 2 is 0, and 5 minus 4 is 1. So something interesting happened here. We've actually, in trying to eliminate the first term in a row, we've eliminated our leading one as well. There's no way we can make this a 1 because it's a 0 and you can't really multiply or divide 0 by anything to change it. So we're kind of stuck with this 0 here. Whenever you have a coefficient matrix with zeros in a row, you're either in the case that there is no solutions to this system or there are infinite solutions. Once again, I'll repeat that because it's important. When you have 2 zeros in the coefficient matrix in a row, or any number of zeros in a row, you're either in the case that there's no solution to this system of equations or infinite solutions to this system of equations. Now, the way you can identify it is if the row that's adjoined, that's after these dotted lines here, is also a 0, then you would have infinite solutions. But here we're dealing with a case where there's no solutions. Because if we were to write these equations out, we would get, well, starting from the last row, 0 is equal to 1, and x plus y is equal to 2. So no matter what we set x and y equal to, this equation will just never be true. So since this equation is never true, this system of linear equations has no solution. Once you put a matrix into row echelon form and you see something like this where you have some zeros and a 1 or any other number here, you automatically, since 0 can't be equal to anything else but 0, you automatically have no solution. Let's try applying the same logic to this 3 by 3 and see how the row echelon form compares. So first we need to write out the matrix, and you should have plenty of practice with this already. So I'm just going to go very quickly to -4, 1, and we adjoin a 3, 8, -2, 4, and a 7, -4, 1, -2, and a -14. Okay, so this is the coefficient matrix right here, and we added on what each of these equations are equal to. So let's go ahead and put this in row echelon form. So the first thing we do here is we divide the first row by 2 to create our first leading one. So let's go ahead and do that. Let's divide our first row by 2. Since this term's a 2, this will create the leading one. So 1/2 row 1, and let's make that the row 1 in our final matrix. So doing that will get us, so 2 divided by 2 is 1, -4 over 2 is -2, 1 over 2 is 1 over 2, let me write it like this, and 3 over 2 is 3 over 2. Okay, that's our first row. And since we're only affecting the first row, the rest of the rows stay the same. So 8, -2, 4, 7, -4, 1, -2, -14. So this is our resulting matrix after applying this elementary operation. So we've created our first leading one. Let's go ahead and create our second leading one. But before doing that, we need to eliminate any terms that come before it in the row. So in this case, the 8. I look in this column and I see we have a leading one above it. So we can probably subtract 8 times row 1 from row 2 in order to create our second, in order to eliminate this term to create our second leading one. So let's do that. So let's subtract 8 times row 1 from row 2. So row 2 minus 8 times row 1. And of course, we're going to replace row 2. So since we're only affecting row 2, row 1 stays the same. So row 2 minus 8 times row 1, just like I intended, 8 minus 8 is 0, so we eliminate this term. -2, well, -2 times -8 is plus 16. So -2 plus 16 is 14, right? Because -2 minus 8 times -2, well, that's 16, and -2. Yep, 14. And then 4 minus, well, this will just be 0 again, because 4 minus 8 over 2, which is 4, is 0. And here we're left with 7 minus 8 over 2, which is 7 minus 4, which is 3. And the last row will stay the same since we're only affecting the second row of our matrix. Yep. Okay, so now we can divide, to create our second leading one, we can divide the entire second row of our matrix by 14, because that will create our second leading one. And doing that, so that would be 1 over 14 times row 2, and we're replacing row 2 in our resulting matrix. So the first row stays the same, 1, -2, 1 over 2, 3 over 2. The second row is 0 over 14, which is 0, 14 over 14, which is 1, 0 over 14, which is 0, and 3 over 14, which we can't really simplify. Okay, and the third row stays the same since we're only affecting the second row of our matrix. So I can do a better job than that. Okay, now we arrive at the last row of our matrix. So for the last row, it's pretty much the same idea, but here we just have to eliminate the first two terms. So we can do that. Well, we go up this column, we see a leading one in the first row, so we can probably add 4 times the first row to the third row and eliminate this -4. So let's do that. So that would be row 3 plus 4 times row 1, and here we're replacing row 3, which, well, all of these rows stay the same. So the thing about this method is it's really just practice, getting good at applying Gaussian elimination. If you can practice and you get good at this and you can apply it on your own, like without you watching this video and me telling you exactly what to do, you pretty much got it. But it's very crucial that you actually understand it through practice. Because I can sit here and do this all day, but if you don't understand how to do it, then you're in trouble. So -4 plus 4, just like we intended, that's 0. 1 plus 4, well, that's, or sorry, 1 minus 8, well, 1 times, so 1 minus, sorry, but yeah, that's 1 minus minus 8, so that's 9, minus 2, which is -4, so -2, or sorry, -2 plus 2, which is 0, 1 minus 8, okay. Sorry about that. I made a tiny arithmetic error here. So it says 1 minus 8, which is -7, minus 2 plus 2, which is 0, and minus 14 plus, well, 12 over 2 is 6. So this will become -14 plus 6. So 6, and that should just be -8. Okay, so this is our, after we apply this step, this is what we get. And already you can see that we lost our last leading one. So this is going to probably lead to the case where we have no solutions or infinite solutions. But we just have to keep moving and see what happens. So now we can eliminate this term and see if this becomes a 0, then we'll have the case of infinite solutions. But if this doesn't become 0, then we'll have the case of no solutions, which we know is what's going to happen because I told you. So to eliminate this -7, we go up this column, we see a 1 here. If we add 7 times this row to this row, then we can eliminate this -7. So let's do that. So row 3 plus 7 times row 2, and of course replacing row 3 in our resulting matrix will get us the following matrix. So 1, -2, 1 over 2, and 3 over 2 stay the same. This row stays the same. Here we have what we're looking for. So 0 plus 0 is 0, -7 plus 7 is 0, this stays at 0, and here's what's important. So we're going to get -8 plus 21 over 14. So here we ran into a problem. So the reason that this is a case where there's no solution, and the reason that I didn't actually write out what this is numerically, well, -8 plus 21 over 14. This is going to become like 7 times 3. This is going to become 7 times 2. So we'll have like 3 over 2, so 1.5. So this will become 6.5. We're going to have 6.5 here. I'll just write that out, 6.5. Or -6.5 rather. So we're going to have 0 is equal to -6.5. Now, since this is just never true, we have the case where we have no solutions. And this compares to our 2x2 system, because if we look at our 2x2 system, let me just find it. I think it's up here. Yep. So in our 2x2 system, we also got something like this. We got 0 is equal to 1. We had 2 zeros in the coefficient matrix, and on the column we added on, we had a non-zero number. Similarly here, we had zeros in our coefficient matrix, and in our column that we added on, we had another non-zero number. So this non-zero number here can never equal 0, no matter what x, y, or z equals. Since no matter what we set our variables equal to, we can't satisfy this last equation. We get the case where there's no solution. So once again, this matrix has no solution. And when a system of equations has no solution, we're done. We can't do anything more, obviously, because there's nothing to be done. We've just proved that since we can never satisfy one of the equations in the system of equations, we can't do anything. We can't solve the system. So we can just say we have no solution.